In Chapter 6, we will be looking at organic reactions, and we will be discussing the types of organic reactions that we see, and we'll be looking at thermodynamics and kinetics and transition states. So there's lots of interesting things to talk about in this chapter. So first, when we're writing out equations for organic reactions, we want to make sure that we have the right components. We'll have our starting materials over on the left, and the products will be over on the right. They will be separated by an arrow. Down here, I've got a few examples of starting materials. The starting material here is cyclohexene, and our products on both of these, as they're written, is 1,2-dibromocyclohexene. And then, of course, the arrow is in between. We've got reagents. Reagents are chemicals that we add to our starting material. Technically, a reagent and a starting material, those are both reactants. But the reagent, usually the starting material is something that's organic, and the reagents are the things that we add to it to do modifications to our organic chemical. Sometimes we can put those right next to the arrow, and sometimes you'll see when organic chemists are writing this, they'll put it on top of the arrow. Either one of those is legit and a valid way of writing them. All right. Usually the reaction will take place in a solvent, but sometimes that solvent is omitted unless it has a particular impact on the mechanism of the reaction. We'll see that in the next chapter, in Chapter 7, where solvent will have an effect on which mechanism happens. So here, for example, we've got carbon tetrachloride is the solvent. And then sometimes we'll have special parameters like you have to add light or heat to get the reaction to work. We also have what we refer to as sequential reactions, reactions that happen one right after another. When two sequential reactions happen, the steps are numbered either above or below the reaction arrow. And here is an example. This is called a Grignard reaction. We don't see this until second semester. But here on the left, we've got acetone. When we add this Grignard reagent, CH3MgBr, to the acetone, it reacts and it gives us a intermediate. And then we add water, and the water reacts with that intermediate. If you were to add these two chemicals at the same time, these two things would react with each other before they ever had a chance to react with the acetone. So it's important to pay attention to those numbers, because often we purposely don't add them at the same time because it would mess up the reaction. All right, so we're going to look at the different types of organic reactions, at least some broad categories. Substitution reactions, this is one type of reaction that we will be talking about in the next chapter. Substitution reaction, we replace one atom with another atom. Usually what's involved is that we're breaking a sigma bond and replacing the atom with a new sigma bond. And here is the reaction. Sometimes the thing that we're replacing is either a heteroatom, but sometimes it is hydrogen. It just depends on what kind of substitution reaction we are doing. And the fact that it's a substitution reaction doesn't necessarily tell us what the mechanism of the reaction is. There are different mechanisms that will give us substitutions. So here are a couple of examples of substitution. In this example, we're replacing an iodine atom with a chlorine atom. So you'll see chlorine comes in and the iodine is lost, and we end up with this chloromethane and iodide. In this case, we're replacing the chlorine with the OH group, and we'll end up with the chloride as our leaving group. So again, these are just substitution reactions. The mechanisms for these reactions are completely different. And again, I want to emphasize that the fact that it's substitution doesn't necessarily tell us that it's one particular mechanism or another. All right, so kinds of organic reactions. We've got elimination reactions. In addition to our substitution, we have elimination reactions. In an elimination reaction, our starting material you'll have some elements that are lost from the starting material, and you'll form a pi bond. Here is an example. So we can lose XY across a carbon-carbon bond, and we form a pi bond across those two carbons. And then XY is a product. Sometimes that product is interacting with the reagent. There's all kinds of ways that this can happen, but it is a there's again all kinds of possible mechanisms that we can do with that particular thing. Let's look at a couple of examples of elimination. Here we've got two sigma bonds broken, and then a pi bond is formed. The most common example, and the one that we will be looking at in, I'm trying to remember which chapter. It's either 9 or 10, or could be 11, but it's coming up, where we lose HBr, or an alkyl halide, across a carbon-carbon bond, and we form a new pi bond, and this is called an elimination reaction. And now that I think about it, I know this is in chapter 8, so coming up soon. All right, so we lose this across the carbon-carbon bond and form a new pi bond, and then here is our product, and we also have bromide. This one is a slightly different mechanism. I think we're going to look at this one in chapter 9. It's also an elimination reaction, but instead of using a base, we're using an acid. So it has a slightly different mechanism, but it's the same basic idea. All right, so kinds of organic reactions include addition reactions. All right, so addition reactions are where elements are added to the starting material, and typically we're going to add two elements or two groups across a carbon-carbon double bond. So the pi bond will be broken, and we'll get two new sigma bonds. So here we're going to add X and Y across the carbon-carbon bond, and we end up getting two new sigma bonds where X is bonded to one carbon and Y is bonded to another carbon. There are lots and lots of possibilities for us to look at in this, and we will see this coming up. I believe this one's in chapter 9. All right, and then here is an example of an addition reaction. We can add HBr across this carbon-carbon double bond, and we'll get hydrogen connected to one carbon, bromine connected to another. This one, we're going to add water across a carbon-carbon double bond. We'll get hydrogen bonded to one of the atoms and the OH bonded to the other atom. All right, so we're going to look at number 26. Number 26 is really easy. So number 26 is really easy. So classify each transformation as substitution, elimination, or addition. So here we don't have a double bond, and here we do have a double bond. So this is an elimination. All right. Here we've got a cyclohexene. There on this carbon there are two hydrogens, and on this carbon there's one hydrogen and one chlorine. So we've replaced one of the hydrogens with a chlorine. That is a substitution. All right. Here we've got a double bond, and here we don't have the double bond. You'll see on this one we have no atoms attached to the oxygen other than the carbon, of course. And on the carbon there are no hydrogen atoms, but here we've got a hydrogen atom on the carbon and a hydrogen atom on the oxygen. So we've added H2 across that carbon-oxygen double bond. That is an addition reaction. All right, and then here we've got, let's see, we've got a carbon-chlorine bond, and we replace that with a hydrogen, and so this is a substitution. All right, so that is a substitution reaction. All right, so just one more quick note about this. Addition and elimination reactions are essentially opposites. And sometimes we can find that we can get the reaction to proceed either way simply by just changing the conditions. So they're essentially the exact opposites. Pi bond is formed in the elimination reaction, where a pi bond is broken in the addition reaction. As I mentioned, these are often reversible. So in the elimination reaction, we form the pi bond, and the addition reaction, we get rid of the pi bond. All right, so now we want to look at section 3, where we talk about bond breaking and bond making. So bond breaking and bond making. Reaction mechanism is a detailed description, and learning to draw out reaction mechanisms is an important component of organic chemistry. So we will find that there are two types of reaction mechanisms that we will look at. And those two types of mechanisms are either going to be concerted mechanisms, where the reaction occurs all in one step, or we can have stepwise mechanisms where the reaction occurs in a series of steps. Sometimes it's 2, sometimes it's 3, sometimes it's 10 steps. But it is a series of steps. We'll find that there are two types of bond breaking. We can have bond breaking that is called homolytic bond breaking, and this is where the electrons are divided equally. I'll show that to you here in just a moment. And we have heterolytic, where the electrons are divided unequally. Since there are two electrons in a bond, you can either have one electron go to each atom, or you can have both electrons go to one particular atom. And so that's the difference between homolytic cleavage and heterolytic cleavage. All right, so homolytic bond cleavage. All right, so homolytic bond cleavage, the electrons are divided equally between the two atoms. So if you have one pair of electrons, one of the electrons goes to one atom and one of the electrons goes to the other atom. This will generate uncharged reactive intermediates, and we will refer to those intermediates as radicals. So here is a reaction where an A-B bond, we don't know what A and B are, but an A-B bond is broken, and one electron goes to A and one electron goes to B, and we end up with radicals on each of those atoms. All right. In heterolytic cleavage, as we just described, they are divided, they are unequal. All right, and I think I just said these exact same two things. Oh, and heterolytic, these are different. This is heterolytic. I read the word wrong. So heterolytic cleavage, the electrons are unequally divided. So in this case, both electrons will go to one atom, and the other atom won't get the electrons. When we do this, we're going to generate reactive intermediates. We'll get, if they're carbons, they'll be carbocations, the positively charged carbons. And if they're anions, they will be carbanions. Usually the electrons will end up on the more electronegative atom. And so here is an example of how that works. So here we've got two atoms, and they're connected by one bond. That one bond represents two electrons. If both of those electrons go to atom B, we'll get this top scenario where we'll get a positive charge on A and a negative charge on B. If both of those electrons go to A, we'll end up with a negative charge on A and a positive charge on B. Our curved arrow notation for bond cleavage is going to depend on what kind of bond cleavage we have. If it is homolytic bond cleavage, we'll have one electron going to each atom. All right, so for homolytic, we have one electron going to each atom, and we will use the half-headed curved arrow. Sometimes it's called a fishhook because it kind of looks like a fishhook, although the barb is going the wrong way for that to be a fishhook, but that doesn't really matter. So here we go, one electron We use half-headed to indicate the single electron is going to A and a single electron is going to B, and we generate those radicals. For the heterolytic, we'll use a full-headed arrow. We've used this already. The full-headed arrow is where 2 electrons are going to move, and in this case we have it going to atom B, but it could easily go to atom A if that were what the reaction we're doing. So just use the appropriate arrow with the appropriate type of reaction. We can generate different kinds of reactive intermediates when we do bond breaking. So if we do homolytic cleavage or homolysis, with homolytic cleavage, we end up having 1 electron going to the carbon, 1 electron going to the other atom, whatever it happens to be, and we will get a radical that is formed. All right, and that is a reactive intermediate. A radical, this reactive intermediate, this carbon radical, if you count the electrons, there's 2 electrons in each bond, so that's 6, and then 1 additional electron that is unpaired there. That gives us a total of 7 electrons around that carbon. That means that carbon is electron deficient, and it is electrophilic. It wants more electrons. Similarly, if we do heterolysis, where we break the bond, but both of the electrons go with our leaving group, we'll talk about leaving groups in the next chapter. Both of our electrons go with a leaving group, then we end up with a carbocation. That carbocation only has 6 electrons around it, and it is also seeking out electrons, and so it is also an electrophile. And then in our final category, if both of the electrons go to the carbon, and this can happen particularly if Z is like hydrogen and you have something come along that can deprotonate it, then you will get a carbanion, and it has 8 electrons around it. It is electron rich because it's negative, and it will be considered a nucleophile. So the same carbon atom can give you a radical, it can give you a carbocation, it can give you a carbanion, and these things will behave differently depending on the conditions. All right, so we want to look at bond formation. There are 2 modes of bond formation. If we have radicals come together, they can donate 1 electron each. So you just draw a half-headed arrow to some position in the middle, another half-headed arrow to that same position in the middle, and that indicates that we're forming a bond in between them. If we have an anion and a cation, we can donate the electrons from the anion to the cation, and in doing that, we will form a bond in between. We'll find that bond formation is always going to release energy. All right, so we're going to look at number 26. So here we want to use either full-headed or half-headed arrows, curved arrows, to show the movement of electrons. And in doing this, we just need to pay attention to what it is that is actually changing. All right, so you'll see here that we've got a bond between the bromine and carbon, and over here we've got a positive charge on the carbon and a negative charge on the bromine. So that's the bromide ion. That means that both of the electrons that were in that bond went with the bromine. So we're going to draw an arrow from the bond to the bromine atom, and make sure that you use the full-headed arrow. All right. So that was pretty easy. All right, and then here we've got, so we look at what bonds we have here. We've got carbon-carbon, carbon-carbon, carbon-chlorine, carbon-oxygen. And then over here, we've got a double bond between the carbon and the oxygen. So we've got a double bond. If we look over here, we have a negative charge, and then here we don't. Here the negative charge is on the chlorine. If you have a negative charge and you're going to something that doesn't have a charge, it's usually best to start with that negative charge to start pushing the arrows. So for example, on this, we've got the oxygen. There's 3 pairs of, or 3 unpaired electrons on that, or 3 paired electrons, 3 pair of electrons on that oxygen, and we're going to go from that to the carbon-oxygen bond to make the second bond. Now, we can't stop there, because if we stop there, we've already got 4 bonds going to carbon. We would have a 5th bond. And 5 bonds going to carbon is verboten, so we cannot do that. So we're going to take the bond between carbon and chlorine and go out to the chlorine atom, and that will give us the chloride. All right, on this next one, we've got a carbon radical and a chlorine radical. And so those are going to come together to make a carbon-chlorine bond. So we're going to take the 1 electron here and draw an arrow there. And we'll take 1 electron here and draw an arrow there. And I like to come at it from different sides because I think it looks pretty, but it doesn't really matter. If you look at it like it showed on the example from the lecture, they come at it from the same side. But it doesn't particularly matter. All right, on this one, we've got a carbon radical, and then you'll notice we have bromine here, and we're going to make a new bond between carbon and bromine, and we'll have a bromine radical when we're done. I find it useful when you've got this to go ahead and draw the bromine. So go ahead and draw the bromine with its bond. All right, we do have all these lone pairs around there, and you can draw those if you wish. Okay, and we're going to make a new bond between carbon and bromine. Since carbon already has 1 electron, we can do a fishhook arrow to one place there. And then we'll take one of the electrons that's in the bromine-bromine bond, and we'll do a fishhook there to the same point. All right, and those got a little close, but anyway, there's 2 fishhooks there. And then we're going to take one of the electrons and do a fishhook to the bromine atom. And that will give us the electrons in the right place. Okay, on this one, we'll see that we've got, for some reason the type is really small here, but we've got a carbon-bromine bond and then hydroxide, and over here we've got a carbon-oxygen bond and bromide. So we're making a new bond between the carbon and oxygen. If you're not sure where to start with a negative charge. So we're going to make a new bond between that oxygen and carbon. Since it's a negative charge, we're going to use the full-headed arrow. There is a bond between the carbon and the bromine. And I'm going to go ahead and redraw this. CH3, CH2, bromine. And so you'd go to that carbon, and then from here, we're going to go from that bond to the bromine. You'll see since the bond isn't drawn there, that makes it a little bit difficult to indicate that we're using that bond. So from the bond to the bromine, and that will give us this. All right, here we're breaking a bond between carbon and hydrogen, and we're making a new bond between carbon and carbon, a pi bond, and we're making a new bond between oxygen and hydrogen. So again, if you're not sure where to start at the negative charge. So we'll go from the oxygen to one of the hydrogens. It doesn't matter which one we pick. They're all equivalent. And then we're going to take that pair of electrons that's in that bond, and we will make it the pi bond. So it will be that second bond between those 2 carbons. All right. After doing this for a while, you are going to get very familiar with it. Okay, so for the different types of organic reactions, we have different arrows. For a regular reaction where we just have a starting material that is going to a product, then we just use a single reaction arrow that has a double head on the end, so the full head rather. So so that's the reaction arrow. And again, this is just used between starting materials and products. If you've got the double arrows, that indicates an equilibrium process. It's almost always okay if you put the double arrows. I mean, there are some situations where you won't have the double arrows, but it usually is okay if you put the double arrows in a particular reaction. Then the double-headed arrow is only used for resonance structures. We did talk about resonance structures in earlier chapters, and we will see more resonance structures. They are not going away. And then, as we have talked about in this chapter, we've got the full-headed arrow that we saw when we did resonance structures, and the half-headed arrow, the half-headed curved arrow, when we're talking about the movement of a single electron. All right, so now we want to look at section 4, where we are going to discuss bond dissociation energy. And bond dissociation energy, or bond enthalpy, is the energy needed to homolytically cleave a covalent bond. All right, so the bond dissociation energy is that. Homolysis does require energy, so it is going to be an endothermic quantity. So bond breaking always requires energy, and so bond dissociation energies are always positive, and homolysis will always be endothermic. That means if bond formation is always going to release energy and will always be exothermic. So in this case, we're breaking this, and it is making the two new atoms, and as I mentioned, that is always going to be an endothermic step. Here is an example of bond breaking and bond making. You'll see that the bond breaking is endothermic. It's positive 435 kilojoules per mole. And then if we take the two hydrogen radicals here and we bring those together, that's going to make a new bond, and that's negative 435 kilojoules per mole. So always think of bond breaking as positive and bond making as negative. All right, here is a table of some bond energies. And these bond energies are mostly between carbon and hydrogen, or between carbon and a heteroatom, or there are a few carbon bonds in here. I don't have any multiple bonds in here, but we'll talk about those briefly. So a couple of patterns that I want you to recognize. All right, so the first thing I want to point out is that the larger the number here, the higher, the stronger the bond. So the larger the bond dissociation energy, the stronger the bond. So things with stronger bonds tend to be more stable than things with weaker bonds. And you'll notice that there are two different numbers here. There are kilojoules per mole and kilocalories per mole. There are a lot of organic chemists who still use the kilocalories per mole. I learned kilocalories per mole. I memorized all these numbers as kilocalories per mole, and now I'm rememorizing them as kilojoules per mole because that's what you're supposed to use. No big deal, but there are the numbers. We'll find that, generally speaking, shorter bonds are stronger bonds. And just as an example of that, if you look at CH3F, CH3Cl, CH3Br, and CH3I, as you go down that column, this is going down the group 7, so fluorine, chlorine, bromine, and iodine. And as you go down, those get bigger atoms, and so the bonds get longer, and you'll see that they get weaker. One other thing that I wanted to point out here is that multiple bonds tend to be stronger than single bonds. So a double is stronger than a single, and a triple is usually stronger than a double bond. So multiple bonds tend to be stronger than single bonds. So let's look at number 32. All right, so here's number 32. Rank each of the indicated bonds in order of increasing bond dissociation energy. So we want to go from the weakest to the strongest. Well, here we've got carbon CCl3, and then it's bonded to some other halogen. So we'll go from the longest bond, which would be iodine, That would be the weakest, and then stronger than that would be the bromine, and stronger than that would be the chlorine. And then almost certainly, if we had a fluorine, it would be even stronger. And then if we look at these, here we've got a triple bond, a double bond, and a single bond. And so the weakest of these would be the single bond. And then our double bond. And then our triple bond would be the strongest. Now we want to look at how we use these numbers. Well, we can use these numbers to estimate the enthalpy change in a reaction. And it is just an estimate, and I'll talk about why it is just an estimate here in a little bit. All right, so if we take the sum of all the bonds that are broken and subtract away the sum of all the bonds that are formed, we will get an estimate of the overall enthalpy change. We will find, and we'll talk about this a little bit later, that reactions that are exothermic tend to be a little bit more favorable than reactions that are endothermic. So this is usually the reason that we're doing this, is because exothermic reactions are more favorable. All right, when delta H is positive, that would indicate that we have an endothermic reaction. The bonds that are broken were stronger than the bonds that we made. We can do this, but there usually is a cost somewhere else. If delta H is negative, then we get more energy released from the bonds that we formed than from the bonds that we broke. So our product bonds are stronger than our starting material. All right, and then delta H positive, that means endothermic, and delta H negative is exothermic. So looking at an example of calculating delta H, all right, so here we've got a reaction where we are turning this, let's see, T-butyl chloride plus water into T-butyl alcohol plus HCl. All right, if we look at the bonds that are broken, we break this carbon-chlorine bond. We break an oxygen-hydrogen bond. We make a carbon-oxygen bond, and we also make a hydrogen-chlorine bond. All right, so these are the bonds that we broke, so these will be positive. And then here I just put a negative here to subtract away the bonds that were formed. In the textbook, it would just make these negative numbers, but I recommend just adding together all the bonds that are formed and then subtracting that whole list. All right, and so we're making a carbon-oxygen bond, and we're also making the hydrogen-chlorine bond. Now you'll notice that I have in particular picked, this is a tertiary carbon, and we have different numbers for like a tertiary carbon bonded to a chlorine than we do for a secondary carbon bonded to a chlorine. We'll talk about why that's true later in not today, but later in the semester. So what I want to do is I'm opening up the appendix that has these values in it, and we're going to look for our carbon chlorine where it's a tertiary carbon. All right, so these are hydrogen, and there it is. So CH3 3CCl, and that one is worth 331 kilojoules. So you might want to jot that one down. So 331 kilojoules. And then an HOH, that is the bond in the hydrogen-oxygen bond in water, and it's worth 498. So that one's worth 498. Let's scroll over here. We've got a carbon-oxygen bond, so it's the tertiary alcohol. And we'll scroll down and we'll find it. There it is. So that one is worth 401. And then this one, the HCl, it is worth 431. So I'm going to minimize that and you put all those numbers in. So 331, 498, 401, and 431. When we add these together, we get 829. These add together to give us 832. 829 minus 832 gives us negative 3 kilojoules. Now, I would not be comfortable saying absolutely that this is going to be an exothermic reaction. Maybe it's slightly exothermic. There are so many limitations. There's so many limitations when you're doing this that I would just say it's risky. It is risky to assume that you are going to have that it's going to be perfect. And I'll talk about the limitations in a bit. But it is slightly exothermic. Generally speaking, exothermic reactions are more favorable than endothermic reactions. If it's slightly exothermic, 3 kilojoules, there can be as much uncertainty as 10, sometimes even 15 kilojoules in these calculations. So I wouldn't be super confident, but it's going to be better than if it were positive 3 as far as your chances of being able to do the reaction. Okay, so that's 6.33 is the problem that we want to do. And before I switch over, I'm going to pause for a second. All right, well, I have set up my camera here. All right, so there is the problem, and then okay, so there we go. I've got that. So there we go. And so here we've got these, so I can look at those bond energies, and we've just got the kilojoules per mole there. So let's go through this. So here we've got CH3, CH3 plus Br2 gives us CH3, CH2, Br plus HBr. So the bonds that are broken, we're going to calculate this, our bonds that are broken are going to be the CH3, CH2H and a bromine. And the bonds that are formed are going to be a CH3, CH2, Br, and an HBr. So when we're calculating that, we'll look for, let's go ahead. We got the HBr right there, so I'll go ahead and put that one in. That one is, what is that, 368. And then our bromine is right there at 192. So 192 is there. And then let's scroll down and we'll find the ethyl hydrogen, which is this one, at 410. And then here we've got the CH3, CH2, Br. And it's right there, and it's at 285. All right, so to do this calculation, I'll get my calculator out. Okay, so 410 plus 192. All right, and that's 602 minus, we'll do the sum of this, so 285 plus 368, and that gives us 653. So 602 minus 653 gives us negative 51. So negative 51 kilojoules per mole. So that, we would predict that one is going to be exothermic. All right, let's look at this one. Delta H. We're breaking a carbon hydrogen, so we'll have a CH3H, and that's the only one we're breaking. And we're going to be making an HOH. All right. So since those are the, we're only breaking one bond and we're making one other bond, that's all we need to consider. So our CH3OH is right there. All right, CH3H at 435. And then the HOH, it's the water, and it's at 498. So 435. Go ahead and put that right there. 435 minus 498, and that gives us negative 63. So negative 63 kilojoules per mole. Okay, let's look at the next one. So here we've got CH3OH plus HBr gives us CH3Br plus H2O. We're going to be breaking a carbon-oxygen bond and the hydrogen-bromine bond, and we're going to be making a carbon-bromine bond and a hydrogen-oxygen bond in water. So our delta H is equal to CH3OH plus the HBr, and then we're going to make the CH3Br bond plus the HOH bond. And we just need to find the values for this. So CH3OH it's right there at 398, 389 rather. Okay, plus the HBr. We did the HBr earlier. It is 368. All right, and then we're going to subtract away the CH3Br. That's at 293. And then the HOH, we saw that one a minute ago, was 498. All right, so 389 plus 368. 757 minus 293 plus 498, so minus 791. Negative 34 kilojoules per mole. All right, we'll do this one more, and that will be the end of this particular problem. All right, so we're breaking a carbon-hydrogen bond. In methane, so CH3H. That's the only bond that we're breaking. And then we're making a CH3Br. So we're breaking this one and making this one. The bond that we broke, the CH3H, we already did that one. That one was 435. And then the CH3Br, we just looked at that one. That one was 293. right? That was 293. And that one, that's going to give us a positive number. Minus 293. 142. So positive 142 kilojoules per mole. What that tells you is that this reaction, as it's written, is probably not going to work. So it is not going to work. Okay. Before we stop this video, I want to do the last little bit of this section, and then we'll stop the video and we'll start up the next section. So here I just want to show you that one of the common reactions we see for alkanes is if we just burn them. So if we take an alkane like isooctane, which is a component of gasoline, and we burn it, you'll see that it releases quite a bit of energy. So negative 5447 kilojoules per mole. It's quite exothermic, but that's exactly what we expect when we're burning things. If we burn glucose, you'll notice that we don't get as much energy, and the biggest reason for that is that we're not producing as much water, and a big reason for that is because it's already oxidized some. So we'll find that for most organic chemicals, we should get a significantly large exothermic number, so a significantly large negative number here. However, the size of that number is going to depend on a variety of factors like how oxidized everything already is. If you have a whole bunch of carbon-chlorine bonds or something like that in there, your chances of the reaction working are a little bit less. So, and we'll find that the more oxidized it is, the less heat is going to be released. All right, and then now let's just real briefly talk about some of the limitations of bond enthalpy values. So that table, what makes it useful is that we can estimate the enthalpy of reactions. But what its limitations are is that it doesn't tell us anything about the mechanism or how fast the reaction goes. All it tells us is the energy difference. And so that is that's something that we have to consider. It also is important to know that all of these numbers are determined for reactions that are in the gas phase. Well, in the lab, we don't often do gas phase reactions just for normal, laboratory work. We often have a solvent, and this completely ignores solvent effects. So we probably need to keep that in mind, that sometimes the solvent effects can be quite significant. And then finally, these are imperfect indicators of energy changes. They are something to get you in the right ballpark so that you can estimate whether a reaction has a chance of happening. That said, we find them very, very useful. So, all right, next thing we're going to be talking about is thermodynamics, and I know you're excited about that. I certainly am. So stay tuned for the next video.